Yeah, okay. Well, I think... ¿Esperamos tantito más? What?
Yo creo que podemos ir empezando, ¿no,
Sí,
Javier?
sí, empezamos ya. Okay.
Pero, permítame. ¿Ya está grabando?
Sí.
Listo. Ya está grabando.
Okay. Well, hello. It's a pleasure to have with us here today Pavel Kroupa, Dr. Pavel Kroupa, whom many people probably know or at least have heard of or read his papers. He did his PhD at the Institute of Astronomy in Cambridge under the direction of Dr. Jerry Gilmore about a year and a half before I got there. So we just missed each other there. During his PhD, he really introduced sort of formal probabilistic scheme to derive the IMF, and that's what he's most well known for. This work was later developed during his postdocs in Kiev, no? Kiev and
Kiel, yeah, northern Germany. Yes.
Yeah, Kiel, right. That scheme has more recently been extended, or it's already about 20 years, into the sort of integrated galactic IMF formalism, which is obviously his most well-known work. But he's also done, well, ever since, about 20 years ago or so, you've held joint positions in Bonn and Prague, the Institute of Astronomy in Bonn and the Charles University in Prague. And he's also been very active over the past 20 years or so in poking holes into the standard scenario and looking at alternative gravity schemes, which is a bit what he's going to be talking about today. So please, just a final comment. He will be here in the Institute until Monday. So Monday he'll still be around, and he's in the visitor's office 209 upstairs. And he's always very open and ready to share his views with anyone who's interested. Okay. So
and to learn, you know.
Exactly.
So yeah, pleasure to be here. I'm here for the first time in Mexico City. So for me, it's a new world, and it's very, very exciting and very beautiful. We've had some very nice dinners already. Probably the cuisine from the north, the center, and the south. So it's really very, very enjoyable and very nice. And today I'm going to present a controversial topic, of course. You can imagine that this is highly problematical. It's basically recent progress on dark matter gravitation, the CMB. So let me just begin. The standard model of cosmology, as you all know, is based on two very fundamental assumptions. And the one is that the gravitation, which describes the dynamics of the whole universe, is based on the Einsteinian Newtonian formulation. And the other assumption is that all matter is created in a Big Bang at the beginning of the universe. So these are assumptions which usually people don't talk about, but it's important to state them here, because if we just make these two assumptions and we then construct the model and we confront that with observations, it actually doesn't work. Observations are CMB and, for example, galaxy rotation curves. And so one is forced to introduce three auxiliary assumptions or hypotheses. And these are one is to introduce inflation, the existence of exotic additional matter, which is called dark matter, plus some exotic form of energy, dark energy, which is pulling the universe apart. So I think that is all well known. And important here is also to note that when we talk about dark matter in this context, the dark matter must be particles and can be cold, warm, fuzzy, or axion. It does not matter, because one has to, with this dark matter, whatever it is, explain the rotation curves of galaxies, as well as the dark matter content in little dwarf galaxies. And this constrains basically that all of these particles must have basically the same dynamical effect. Because if they wouldn't, then one would be violating essential observation constraints. So this means we don't have to care really about the details of the dark matter particle. We just have to know that Yes, exactly. So the important part here is that the existence of dark matter, whatever it is the core pillar of the model. And so the question now is, how do we test for this dark matter? Being scientists, we want to verify models. We don't just believe the models, right? And so how can we test for it apart from just looking for the dark matter? And we know that the dark matter particles must only interact gravitationally, because any other interaction must be negligible, because otherwise we would easily find these particles in the laboratory, and they have not been discovered in the laboratory in any direct search experiments. So basically these cross sections must be very small, and we are left with the gravitational property of the particle, which must be there, because otherwise it wouldn't play any role in the universe. So how can we now test for this existence of the dark matter particle, given that also 30 years, 40 years of searchers have not actually discovered any particle, have not verified the existence of the particle? And there is one particularly very robust test, which for a reason I don't fully understand, but that has been ignored largely. And that is what I call the Winnie the Pooh test. And it's based on Chandrasekhar dynamical friction. So it's called Winnie the Pooh test, I call it, because there's a story where Winnie the Pooh uncovers a scam in a village where there's a huge pot of honey, which they claim is invisible honey, so it's very special honey. And Winnie the Pooh invents a method to test whether this is actually honey or whether it's just empty. He discovers it's empty, and then the village expels Winnie the Pooh. So that's basically the story here. And so the test, basically, so this relies, so he throws a little stone in there, and then you can measure whether it clunks down or whether it slowly sinks down. So that's basically the elementary the tests we are also going to apply. So a massive object moving through an invisible fluid will slow down and fall to the bottom slowly. And so this is dynamical friction, which is well known since 1943, which Chandrasekhar published a seminal paper, actually called dynamical friction. This was at that time in the context of a massive object moving through a distribution of background stars. So for example, a black hole, massive black hole, or a star cluster moving through a population of stars, like in the galactic bulge. And so if the standard model of cosmology is correct, then it predicts a new phenomenon. So if dark matter exists, then Chandrasekhar dynamic friction must occur on the dark matter around the galaxy. That's the new phenomenon. So the new phenomenon is that the theory predicts that galaxies have dark matter halos, and so any other galaxy coming in there will now suffer dynamical friction on this dark matter halo before any visible interaction between the galaxies is evident. And that's the new phenomenon. So if there is no dark matter, then this does not occur. If there is dark matter, if the model is correct, then this will be evident in the data, this dynamical friction process. So it works like this. We have here a galaxy moving through a dark matter halo made of these dark matter particles. And what happens is that as the galaxy moves through the dark matter particles, it encounters a dark matter particle. And because this is just a gravitational encounter, this dark matter particle and this galaxy are on a mutual two-body orbit about each other. And so the dark matter particle is gravitationally deflected. At the same time, the galaxy is also gravitationally deflected. So the galaxy moves along, a dark matter particle is deflected, and the galaxy moves a little bit to the right in this particular case. Because momentum is conserved, it means that this velocity vector will now, after the encounter, have a component perpendicular to the motion and a reduced component along that direction. That's just conservation of momentum. And what one does, one integrates over all these encounters. It's just a standard Keplerian orbit type calculations. You find that in any textbook. You integrate over all of these, and you find that these transverse perturbations to the velocity all cancel, because at one point the galaxy goes to the left, because it encounters the particle on the one side. The other side goes to the right, because it has an encounter with a particle on another side. So they cancel. But the systematic, the reduction of the velocity into that direction, that always gets shorter and shorter and shorter the more these encounters there are. Okay, so and that's the dynamical friction. We integrate over all these encounters, and I'm not going to go through the details. This is a presentation based on the derivation by Benjamin-Tremaine. So one basically just solves this two-body problem for one dark matter particle, and then one does many of them, integrates over them. There is a video on YouTube going through this. It is really important. That's why I've made trouble to make that video, because the community must understand this test. Usually the colleagues do not understand the test. And so I'm not going to cover the details here. I'm just going to show you that there is an elementary derivation, which is from Benjamin-Tremaine. If you look at the paper by Chandrasekhar, it's a little bit less easy to go through, or by Spitzer. And this is a very nice derivation which Benjamin-Tremaine have published, which really beautifully demonstrates the effect. And so we have that the galaxy will be decelerated, and that deceleration, you see the minus, is given by this expression, and it depends on the velocity of the galaxy and on the dark matter mass density. And that's the mass of a dark matter particle. And we can then study, given that such a galaxy falls, and imagine it's on a circular orbit in a dark matter halo, it will slowly sink to the center, especially mass segregation. The massive object sinks to the center while the dark matter halo puffs up, absorbs the kinetic energy, and then this time scale on which it sinks to the center, so the merging time scale, is given approximately by this expression, where this is the velocity dispersion of the dark matter halo. That's the mass of the galaxy, that's the initial radius where it starts, and lambda is the Coulomb logarithm. So this is a logarithm, so it's not so important. And the thing is, we have this situation. So we have here the host galaxy, that's the dark matter halo. This is the other galaxy with its dark matter halo, and it enters, and it has a velocity about comparable to the velocity dispersion. That's just, we see that from observations. The galaxies are always with velocities comparable to the actual circular velocity in that potential. And we can then roughly estimate that it takes so many crossing times to actually merge. And that is short. It's remarkably short. So here, for example, if this galaxy has the same mass as this galaxy, it is about half a crossing time. So basically, it falls in. That's it. If the galaxy is 10% of this mass, it's about a crossing time, a dynamical time, basically. And that is, of course, why in the standard model of cosmology, we have rapid buildup of mass, because these dark matter halos which build up, they merge, and they merge very efficiently. And that's how galaxies form and evolve in the standard model of cosmology. And so, so we have this prediction. It's well understood. It's really well understood. So we have basically the host galaxy, dark matter halo, the other galaxy with its dark matter halo, and it produces this sort of wake behind it from these encounters, this deceleration. So the deceleration of this motion vector here is dependent on the dark matter mass density, which is given by the model, so by the CMB. It's not a free parameter. Okay, so this is stuck, and we don't, which means that it's the mass density and not the mass of the particle. This could be black holes of 100 solar masses, it could be black holes of 0.1 solar masses, it could be axions with an incredibly small mass, it can be fuzzy dark matter particles with a very, very small mass too. It doesn't matter, the mass density, and that mass density is fixed by the CMB in the model, by the properties of the CMB. And so here's from Benjamin-Tremaine, just an example of if the ratio of the velocity of the galaxy divided by the velocity dispersion of the dark matter halo is 1, then it's moving through the dark matter halo and leaving this wake of density behind so the density of the dark matter halo is perturbed according to these contours. If it's faster, so this is now 3 times faster than velocity dispersion, the effect reduces. You can see that there's a 1 over v squared effect. Okay, so the faster it moves, the the less important the effect is. But if it's 1, it's basically maximum. So we have the situation, therefore, that this galaxy falls in, touches this dark matter halo, and then this process begins. And so its velocity vector is reduced, there's a wake behind it, and it therefore has to sink in and then merge. And this is why galaxies merge, but only if there is dark matter. Because if there is no dark matter, then this galaxy would just fly past. Just like two stars, nothing would happen, right? Okay, so we have 3 ways of making estimates or calculations. We have this analytical estimate for this time scale it takes from an observed configuration, how long will it take for the system to about merge. Then we can do an actual orbit integration by using this equation in the equations of motion for the deceleration. And we can do an actual full simulation. So we take 2 galaxies in the computer, give them dark matter halos with live particles, and do exactly the same problem. And then we can compare these numbers, just to see whether these estimates and this better estimate and then this actual calculation, how well they agree. And that has been done. Here's just an example from Van den Bosch at Yale University. So you have here the dark matter halo, and this galaxy moves in this dark matter halo of this galaxy, and you can see that it spirals in. So it spirals in, and so this is just the effect we see. Here's now an actual live simulation from Ogier and Burkhardt. So what we are seeing here is the dark matter halo around the galaxy, scaled to dimensionless units. And this is a color scale tells us about the perturbation of the dark matter halo. So the dark matter density decreases outwards, but we divide by the original dark matter density, and therefore it looks like it's a logarithmic scale is basically 1 here. So the density, it's green everywhere because we divide by the NFW density at a particular radius. And so when then the other galaxy comes in, we can see the perturbation in the density. So we can actually see how dynamical friction not only affects the orbit of the galaxy, but in turn feeds back on the structure of the dark matter halo, which of course heats up as a consequence of this process. You can see here now this galaxy comes in. You could see the wake behind it. Red is overdensity. You can see how quickly it merges with the galaxy here. And it takes about 2 to 3 orbits taken from far out. Yeah? So it's very, very efficient. And here's now an actual simulation by Wettstein, Knapp, and Burkhardt to this galaxy. You can see this one encounter, and then they fall together, and the merge is done. And so we apply this Winnie-the-Pooh test now on this triple system. Small, large, Magellanic clouds orbiting the Milky Way. And it's a well understood, well studied system. So we have here the Milky Way. That's the large Magellanic cloud, small Magellanic cloud. This stream in hydrogen gas in red is the Magellanic stream. It spans over the whole sky. And this material in front, which is probably the leading tidal tail. So we know now today, through the Gaia mission, how they are moving to a very good precision. We even know how they rotate internally. It's really remarkable. And so we have these numbers. So for example, so this is just a table telling us the mass of the Milky Way in baryons, and then the dark matter halo mass it must have if it has this baryonic mass. If the lambda CDM theory is true, then this galaxy with that mass must have that sort of dark matter halo mass. And we take a range of these just to allow full uncertainty in these masses. The large Magellanic cloud, the same. We know its baryonic mass from observations of the stars and gas. And so we know what dark matter halo mass it must have if the theory is correct. And the same for the small Magellanic clouds. And we have the position vectors of the 3 galaxies relative to each other. Plus, we have the velocity vectors of the 3 galaxies relative to each other because of the Gaia mission. So the distance large Magellanic cloud Milky Way is about 49 kiloparsecs, small Magellanic cloud Milky Way is 58, SMC LMC is 22 kiloparsecs. And we have the velocities of these systems relative to each other, the galaxies relative to each other. And so if we now apply these simple estimates, then we find that the LMC in the Milky Way halo will merge in about 370 million years up to 1.5 billion years. So it actually doesn't even have really much time to orbit, right? Because it goes in and then really sinks down, because these dark matter halos are massive. I mean, the LMC is something like 10% of the mass of the Milky Way, and that's already very important. The SMC in the LMC halo merges within 260 million years to 1.2 billion years, given the current observation, or that distance, or a significantly larger distance. Now, because, and this is short, because these three galaxies are so close together that they are all within their dark matter halo. So there's a lot of dynamical dissipation. Well, I think there was a question here and then there, maybe, if you want to already. Yeah.
Yeah. Just a question about the dark matter halos of the large and the small Magellanic clouds. Are those numbers that you're checking are at the time of the accretion of the halos, or are the current?
Well, this is all currently happening, right? The LMC and SMC are currently passing, so they fell in about 1 billion years ago.
My question is because normally those models by Peter Beruzzi or others, they quote for subhalos the mass at the time of the accretion. So this is like an upper.
No, this is the current value at Z redshift 0.
We can talk later.
Understand. I mean, the LMC is falling through the dark matter halo now, and it was out of it 500 million years ago. So we are looking at redshift 0.
Right, yeah, now I understand that. I understand that. The thing that I want to say is that those stellar to halo mass relations that Peter Beruzzi...
This is redshift 0.
Right, that Peter Beruzzi publishes.
Nothing before redshift 0, the current configuration. Predictions by the theory for the current configuration, the previous time is not important because we're looking at current situation.
Okay, yeah. Let's talk later.
So
just a detail, what density profiles are you using for the dark matter halos?
NFW.
NFW, without core, just...
Core is not important.
CASP NFW.
Just NFW. Core is not important for these distances. Okay, so the times are short, and so the LMC SMC system should merge very quickly. This graph shows you the gravitational force, which is independent of the velocity. So that's the force versus velocity. A gravitational force between two galaxies, LMC, SMC, at the distance of 10 kiloparsecs, of course, doesn't depend on velocity, but the dynamical friction does. So if the SMC were moving past the LMC very rapidly, then the dynamical friction force would be much smaller than the gravitational force. But at the velocities where we observe they are at, the dynamical friction force is comparable already with the actual gravitational force. So this just demonstrates that the dynamical friction deceleration is very effective. Yeah? And this makes the development of the magnetic stream nearly impossible, because we require, in order to find solutions for the three-body system, such that a magnetic stream can develop, the condition is, which we know from previous work, that the LMC and SMC must have had at least one encounter about 1 to 4 billion years, and this is very, very, very broad range. So they had one encounter 1 to 4 billion years ago. That encounter unbound some of the gas, which then appears as the tidal, back tidal tail, front tidal tail, which we see today as the system is passing the Milky Way. So we need such an encounter between the two in order to create, to unbind gas to make the Magellanic stream. And so we now, Wolfgang Ohm has written a program which searches from the current configuration backwards, integrating backwards in time using the Markov chain Monte Carlo method and the Magellanic algorithm independently, to find all possible solutions such that this condition is fulfilled given the current observed velocities and then a range of masses. And it turns out actually, so these are just the parameters which the search algorithm varies. Given the uncertainties, observational uncertainties, we can then classify whether a solution is within a sigma, 3 sigma, or 5 sigma. And it's, we find, so this here is the integration, so a Markov chain, and this is genetic algorithm. The trajectories of the 3 galaxies, of the 3 pairs of galaxies are shown by the different curves. So this is distance versus time in both cases. And both algorithms, which independently search for solutions, find the same solution. Okay? So this is just a robust validity check that the solutions we find are verified by 2 independent search algorithms, and so they are very robust. We've also tested this integration method with a full-scale live simulation to verify that the search algorithm actually does find the correct trajectories. In the full simulation where the dark matter halos are live, the mergers are more rapid, simply because here we use rigid dark matter halos. If they are live, then there's additional dissipation because the dark matter halo itself gets deformed, heats up, and dark matter is scattered around. So these are conservative solutions. It actually is worse in reality if there is dark matter. And so there are no solutions. Within 5 sigma of the observational data, you do not find a solution that has an account with 1/4 billion years, because when you go backwards in time, the LMC and SMC, they diverge away because dynamical friction is negative, so it accelerates, and there can never be an encounter 1 to 4 billion years ago. However, the situation is far worse than what I've said, because these people in Tenerife have done an analysis of millions of stars in the large and small Magellanic clouds to uncover the star formation histories, going back billions of years. And this is what they found. So this is the star formation rate of the small Magellanic cloud, that's of the large Magellanic cloud. And they see that there are these peaks, and they are correlated. And they are in 4, 1, 2, 3, 4 in 3 billion years. This can only be explained if the LMC and SMC have been orbiting about each other about 4 times. It's actually 5 times, because we currently have another close encounter between the two. So there are something like 4 to 5 encounters in 3 billion years, which means the orbital time, so it's a stable orbit, and the orbital time of these is about 0.75 billion years. And that, of course, is completely impossible if there's dynamical friction, because they would have merged on a much shorter time scale. So you simply can't make an orbit if there's dark matter. And so, so basically this graph now shows the distance versus time of the best solution, given that one condition that you have encountered 1 to 4 billion years ago. That's this red curve and the dashed line between the three pairs. And so this red line here is the LMC SMC distance. They had this encounter just outside of 4 billion years, and then epigalactic perigalacticon now. And this solution is out by more than 5 sigma. So it actually is not a solution, but it's the best you can possibly do given the dynamical friction. It's impossible to have 3 perigalactica to match the star formation history. So you need 3 or 4 perigalactica of the 2 galaxies in order to have the star formation maxima. And all you can at best do is have this one and that one. If you try to squeeze this together, the system just merges. So it's completely impossible to get a solution given these constraints. And this unambiguously tells us there is no dark matter. It is impossible to get a solution if you put dark matter into the system. And we can then check. So this is the solution with dark matter, the orbit decays, so that's the distance versus time. So the 2 galaxies, LMC, SMC orbits decay with time. If we turn off dark matter, we keep the potential, but we simply put the deceleration to 0, then we immediately get solutions. In fact, beautifully, we get about the right number of encounters. And this tells us that you need to keep the potential as if dark matter were there, but you must remove the dynamical friction, so you have to set the density of dark matter particles to 0. And that only works by changing gravitation. Okay? And so further tests, the conclusion here is of course dramatic, and so you want to make sure that the conclusion is truly verified by independent tests. So there are tests using galactic bars, and also all of the satellite galaxies. And that has been done and published. And on galactic bars, I just want to very briefly touch on that. So that's a galactic bar. It's rotating like a rigid body in a galaxy up to the co-rotation point where then the rotation curve becomes flat. That's like a spoon in a coffee. You've got this dark matter halo around it, and this thing, there's a huge amount of mass, is moving around in this dark matter halo, and you take a coffee and you make a thick coffee, you take a hot chocolate, and you see the resistance you find. You let the spoon go and it immediately stops. That's exactly what happens. If there's dark matter halo, this spoon comes to a halt. It stirs up the dark matter halo, but once within a rotation period, basically gets slow, and when it gets slow, it shrinks in size. And so one can now observe galaxies, and we see that real galaxies have fast bars because they have big bars. About 30 to 50% of these galaxies have bars which are long and fast, while dark matter galaxies have slow bars. You look at Eagle simulations, illustrative simulations, you can do exactly the same quantification like you do with the observational galaxies, and you find this. And the discrepancy between the number between these two sets of data sets is 8 sigma. And that's been published by Roshan et al. And again, this tells us there can be no dark matter. You can only sustain such bars if there is no dark matter. You have the potential to make the flat rotation curve, but not the dark matter particles. And so these two independent tests agree. Cosmologically relevant dark matter particles are not present. And that's why they have not been found. You can keep on searching, but you'll never find anything. And remember, the merger tree is an essential mechanism in the smog to grow galaxies, because the dark matter halos merge and because of this Chandrasekhar dynamical friction. However, the same process makes observed galaxy systems impossible to exist. So we looked at compact groups of galaxies, the same problem exists. Therefore, we have the problem that without dynamical friction, because you have to turn off dynamical friction to observe the well-observed systems, but without dynamical frictions, you cannot grow in the standard model of cosmology. You cannot actually make galaxies without this process. So you come to a really serious problem. And there are many other tests performed on the validity of the cosmological model. So here's just a graph where one can summarize these. This is the confidence in the model. It starts off with 1. This is discovery of dark matter, inflation, dark energy. They are not failures, they are discovery of new physics. But then there are issues like core cusp, angular momentum problems, satellite systems, and some of these are 5 sigma falsifications. Overall, if you just very crudely and very, very conservatively sum up the evidence, it tells us that the dark matter-based models are valid with a probability of less than 10 to the minus 130. So I can say that the model is valid, but the probability of that is 10 to the minus 130. And so the standard model of cosmology is the most falsified, but believed to be true model ever in the history of woman, man, mankind. Okay, that's a serious crisis in physics. Not so much that the data tell us there's no dark matter, that's just the scientific process. It was a good idea, very important hypothesis, it's tested, okay, it doesn't work, so we have to move on. The crisis is in the community, because it is not accepted. People continue working on dark matter as if all of that had never been published. That's the crisis. And so the implications are many, but one of these is, are these mergers? I like to ask the students in my lecture that. Typically the argument is, yes, these are mergers. No, they are not mergers. They are encounters, and they might merge in the long distance but they are not now mergers. They're just strong encounters, that's all. It's very important to realize, because you change your language, you don't refer to this as mergers, you refer to this as encounters, then you're in safe waters. So, because there is no dark matter, gravitation cannot be Newtonian. You need to make flat rotation curves, you need to account for the LMC SMC orbit, so that's a logical conclusion. And we therefore now come to this situation. We are now starting to attack this. Well, we've already sort of attacked it. I'm like testing it. And gravitation, is it Newtonian? So the work by Xavier Hernandez, Che, on very wide binaries already tells us that it can't really be Newtonian. There's another nice test using open star clusters. Because star clusters lose mass, the stars evaporate. And so we can test for the shape of the potential created by a star cluster as it orbits a galaxy. And that shape is defined by the theory of gravitation. And so star clusters typically lose mass mostly through evaporation. That's just energy, and the energy equipartition process in the star cluster. The stars move around in the cluster and suffer many little perturbations, and some stars elevate in energy until they are gone. That's well known. So the velocity distribution in a star cluster of stars is something like a Gaussian or a Maxwell-Boltzmann distribution. And there's this high velocity tail which always exists, which are stars which are unbound to the cluster, and they will find an exit. They will leave the cluster, but they don't just leave immediately, because most of the stars are around here, and so they are moving with the cluster with a very small relative velocity, but they are formally unbound. So they are moving with the cluster, seeking to find an exit. And that can be understood very well. So here's, for example, some seminal work by Baumgart and Marquino, where we have the number of the mass in the star cluster divided by its initial mass as a function of time. So here we have these curves. If there were no star cluster, just the stellar population loses mass from stellar evolution for a normal canonical IMF. In the star cluster, the whole object now loses first mass through stellar evolution, but then also the stars evaporate. And how quickly the star loses mass depends on the mass of the cluster, because this is a process governed by energy equipartition, which is then defined through the two-body relaxation time. And we can see, therefore, that each cluster always loses its stars until it's gone. And the interesting thing here is the death of the clusters. They leave highly multiple systems, which are very interesting to study, but that's not the topic here. Now, the evaporated stars leave their open clusters through tidal tails, and we now have a galaxy, and there's a star cluster up here. We're now down here, so we take this box. This box will be the same in the following graphs. So the rotation is in this direction. The galaxy is rotating, so it's moving in that direction, and the galactic center is in that direction. So we now take this box and look at the potential. So you have here this box. We're looking on top of the galaxy. So the galactic center is down here, rotation to that direction. That's the cluster. It has a Lagrange 1 point towards the galactic center, a Lagrange 2 point out of the galaxy cluster, and stars moving around in here, if they are unbound, can only exit through here or through here, unless they are shot out through with a high velocity. And so this can be studied theoretically. How do the stars actually leave the cluster? Because they have very small velocity relative to the cluster. And they typically end up on such orbits. So they do these type of epicyclic orbits relative to the cluster with these turning points. And so we can then look, so that's the same box, that's the cluster, and because of these epicycles, there's overdensities in the tidal tails at regular spacings. This is seen the cluster in the plane. Now, Andreas Kroupa, who was a PhD student with me, discovered with Douglas Heggie these overdensities, which they were not known until his work. And so we have a very nice representation. Where these overdensities are depends on the velocity of the stars as they leave the cluster. So this is again the same box as before. And how do these work? Well, that's been studied now by Jan from Altenburg in Bonn to great detail. So we have the cluster. This is a star which leaves the cluster with a very small velocity, so it does this type of orbit relative to the cluster. The whole thing is moving, but the star slowly leaks out of the cluster, then stops relative to the cluster, and then starts moving again. That's simply because if this is on a perfectly circular orbit, then a star leaving the cluster cannot be on a circular orbit. And so it's on a slightly eccentric orbit, and so the distance between the star and the cluster just oscillates. While the star is moving away, it oscillates, and moves further away, oscillates, just because the star is on an elliptic orbit, slightly elliptical orbit, while the cluster is on a circular orbit. It's exactly the same that's happening in the planetary system, with the planets going forward and backwards. It's the same physics. So depending on the velocity, they either shoot further out or less further out. And some of the trajectories can be complicated. This is an unbound star until it finds an exit. And so all of this is very well understood. We can calculate it theoretically. We can do simulations in the computer, solving the equations of motion very, very precisely with RZEV codes or other codes. And so these overdensities are regular, and the distance from here to the cluster to that overdensity depends on the mass of the cluster and on the galactic potential. So here's a nice simulation. This is a cluster. These are all unbound stars. You can see how they make these overdensities. The same cluster at a time of 6 billion years later, so 5 billion years later than this snapshot, is much less massive because it's lost many more stars. And these overdensities have shrunk to the cluster. So as the cluster evolves, these overdensities shrink to come close to the cluster, and that depends on the mass of the cluster. So if we measure this distance, we get a mass, and we know the mass of the cluster, we can solve for the potential of the galaxy. And that is a very important chance, possibility, and this was published by Küpper et al., global cluster streams as galactic high precision scales. So that's a great chance for people to follow this up and actually map out the potential in 3 dimensions, because these globular clusters are moving around the galaxy in 3 dimensions. And these type of overdensities have indeed been found. And here's, for example, the work by Oudenkirchen et al. Of the cluster PAL5. You can see these overdensities very nicely. Okay, so this is a real method which actually works, but of course you have to find the tidal tails. Now, however, the globular clusters are on orbits which are chaotic. So they are elliptical, and they change the orientation because the potential of the galaxy is not completely spherically symmetric. And so it's difficult to use the tidal tails really to test gravitational theory. And so what we have to do is look at open star clusters which are on circular orbits, and that makes the analysis much simpler. And so we can interpret the tidal tails much more simpler because there's a lot of symmetry if the cluster is on a circular orbit in the galactic disk. Now, Teresa Irabkova, who's also a PhD student with me, discovered a completely new way to map out the clusters, which are called the compact convergent point method. It's a very clever method. She discovered this and actually applied it. And with that, we can now map out the tails of, for example, the Hyades star cluster, which are 45 parsecs away from us, to the tips, basically. And so that's from that paper. Now you notice the star cluster is here on the sky, and these are the tidal tails. So there's evidence of the overdensity, but notice this massive overdensity here. When I saw that, I knew this is a game changer, because the asymmetry between here and there is 6.5 sigma confidence, and it is Mondian. Because you can see this is a Mond model of this cluster, and you can see the same overdensity. And that only is possible if the potential of the cluster is not symmetrical, Newtonian symmetric, but Milgromian asymmetric. And so here is now modern work from Altenburg in Bonn, Newtonian cluster, Mondian cluster at 0 million years, at 250 million years. You can see now there's an actual direct n-body code in Mond and Newton. This is the first time this has ever been done, because nobody had the mathematical capability or methodology to do this. And so we can now study how the tidal tails grow in Newton and Mond. And so you can see, as the time progresses and the cluster orbits around the galaxy, how the tidal tails develop. In Newton, there's a high degree of symmetry. You can already see in Mond a breaking of the symmetry. And so this shows now at 1 billion years that in Mond we have a very long, denser tail than in the back tail, and in Newton they are symmetrical. And so we can now use this symmetry or asymmetry to see whether gravitation is Newtonian or Milgromian. And it works as it's very simple to understand. So we have here the star cluster, it moves up. The galactic center is to the right in this case. If we have Newton, then the force field around the cluster is equal to Newtonian everywhere. So we divide by the Newtonian force, restoring force. A star moving here feels a force going back, and we divide by the Newtonian force, and so it's flat 1 everywhere in the Newtonian case. And so in that case, a star which wants to leave can either leave through the leading tail, so the Lagrangian point 1, or through the second Lagrangian point to the back tail. And in this theory, they are equal within Poisson uncertainties. And this is completely robust. You can do any calculation, that's exactly what you will find. In Mond, because it's a nonlinear theory of gravitation, the potential now is not symmetrical, and we divided each distance from the cluster by the Newtonian value, which we would expect at the distance, and we find that there's a stronger restoring force to the cluster back, so going away from the galaxy, and a little smaller restoring force going out towards the galaxy. This is the galactic center here. And so a star which is unbound is going to more easily exit in this through the Lagrange point 1 than through the Lagrange point 2. That's simply because there is a deeper potential, basically there's a greater potential barrier on this side than on that side. And we expect from this theory that there should be more stars here than in the back tail. Yeah? And indeed, that is what is observed. And we've done this now for 4 different clusters, 6 different teams who published tidal tails on 4 different clusters. So these are the clusters, here are these different teams, Presepe, and then this cluster, and then Coma Berenices too. Leading tail, back tail, and the result is that, so this is the asymmetry. So Jan from Altenburg defined these statistical quantities. This is the asymmetry parameter is variance and the asymmetry significance. So we can see that in the Newtonian expectation, we expect no asymmetry, but of course with some dispersion because of Poisson uncertainties. What we observe is this asymmetry for the 4 clusters. And that's an 8.99 sigma falsification of Newtonian gravitation. And we can do calculations. So this now is a Newtonian, I don't remember what I did here. So this model here is Newtonian tidal tails are in 0.2 sigma tension with Newtonian gravity. So you can see that this is the expectation, just given these quantities and the dispersion, given the number of stars. And the actual calculation of a Newtonian cluster leads to consistency with the theoretical expectation. The tension is 0.2 sigma, which is it's not a tension. So you're testing Newton against Newton, and yes, it works. With the same code now, you're testing now a Milgromian cluster versus the Newtonian expectation, and you find just in the theory a 8.63 sigma asymmetry with more stars in the front tail than the back tail. Remarkable is that this is basically identical. Yeah? And so I think we have gravitation extremely well under control, but it's not Newtonian, it's Milgromian. And so the evaporation of stars from their star clusters unambiguously, compellingly, absolutely falsify Newtonian gravitation. And this is well consistent with what Xavier has already been deducing from the wide binaries, which is on an even smaller scale. Consistency of test results, so we have falsification of cold warm dark matter particles. That was the first part. The second part tells us, and this tells us that the gravitational potential cannot be Newtonian. Don't have dark matter, but you have to have the potential that can only be non-Newtonian. And the tidal tail asymmetry confirms this. So you can see the beautiful logical consistency of this body of research. And so we have seen, therefore, that the Winnie the Pooh test falsifies the existence of dark matter particles. And please redo the calculations. Now, this is a very important scientific statement because it's a fundamental issue in physics. Does dark matter exist or not? Anybody can redo the calculation. Ignoring it is not a solution. And the tidal tails of open star clusters falsify the gravitation Newtonian. Beautifully consistent with each other. And the very core of the smoke is thus kaput. Yeah? And yeah, I'm sorry, but it is therefore not surprising that even the interpretation of the CMB turns out to be fallacious, because I'm telling myself, well, if all of that doesn't work, the whole lambda CDM model is just like it doesn't work, it's been falsified by observation, it doesn't mean that it was a stupid idea. It was a very good idea, important to test, it's been tested, it's out. The question then is, what about the CMB? What role does it play? Is that still valid as a condition, initial condition, for a new cosmological model which we now have to build up? Yeah, that's the question. And so we are now attacking this issue, which is a key observational evidence for the model, but actually for a hot Big Bang model. So we are now starting to approach something which is sacrosanct. I know from many discussions with colleagues that you touch this topic, and for heaven's sake, I mean, luckily I have my permanent position. But as a scientist, I feel obliged to do so because we want to move science forward rather than standing still. And so, is the Planck CMB solution truly universally valid for all models? That is the first step. What is the power spectrum actually telling us about the fluctuations at the redshift of 1100? How do we calculate it from the data? Is it valid for all cosmological models? And it was a discovery, a history of discovery for me, because I was not a CMB expert. The thing is that what we do today is we say the power spectrum extracted from the data by Planck is the initial condition for all cosmological models. Is that so? So this is what one does. That's the initial condition at the redshift 1100, the photosphere of the hot Big Bang. Then we have a model, for example, lambda CDM model. We calculate with linear structure formation to a redshift, say 200. Thereafter, nonlinear structure formation begins. We have to put that into a computer and actually study how galaxies come out of that. Okay, so that's what we then do, using some code, for example, Ramses code or Eagle or so. So that's what one does. Now, if I have another cosmological model, dark matter doesn't exist, so I replace gravitation by Milgromian gravitation. Can I still do this exercise using this initial condition? Everybody in the Mond community tells me, yes, of course, because this is exactly the initial conditions for any cosmological model. And there's stress between me and the Mond community now because of this. The thing is, you cannot do it. And this is what has been done. So this is the power spectrum. Lambda CDM fits extremely well. And this is a Mond model published by Angus Diafore, a very, very important suggestion. It fits also well, very well. So we can reproduce this power spectrum with a model which does not have cold or warm dark matter, but otherwise is very similar to the lambda CDM model. But it has, of course, different types of structure formation and forms a different set of galaxies. And this has been looked at with this paper recently too, by Nick Samaras, who was a PhD student in Prague. So is this correct? Can I look at a different cosmological model, like a Mond-based cosmological model, and use this as the initial condition? And I'm telling you, it is not correct. The reason is very simple, because imagine there's a photosphere of the hot Big Bang which has no fluctuations. Then the photons propagate as the universe is expanding and structures evolve. What happens is that there are deflections through weak lensing, There are changes in energy through scattering on electrons, which accumulate in the forming structures, and the energy changes through evolving potential wells. So if a photon goes in, the potential well evolves like a galaxy cluster, and when the photon exits, the potential wells change a little bit, and so the photon energy has changed a little bit. These three effects lead to fluctuations. So I start with no fluctuations, and I will get fluctuations because of these effects. And furthermore, there's a foreground. There's new sources which appear. They contribute photons, and they also have to be obviously taken into account. So I get fluctuations even if I don't start fluctuations. So what I actually have to do is I take the observations and I have to correct for all these effects, including the foreground, to get the true fluctuations given what I observe and given all these processes. However, these processes are model dependent because I can only correct for these three processes and for a foreground if I know how structures form, but I don't know how they form, I can't observe it, so I have to assume a model for these corrections, I apply the model, and then I get a power spectrum. Now, if I use a different model, like a Mond-based model, these things are completely different because structures form much more rapidly at a different time, at a different scale, mass and spatial scale. So these corrections will all be very different, so when I take the observational data, I correct for this in Mond, I will get a different power spectrum. And that has never been done. We do not know how different that power spectrum will be like, but it's a calculation which actually has to be done. And so it is simply the situation now that the initial conditions at this redshift must be recalculated for every cosmological model separately, which means the whole Mond community, which has been trying to develop Mond cosmological models, is completely off the track because they're using the CMB power spectrum as the initial condition, and that is wrong. And those models also don't work. Yeah? So, however, is the CMB truly the photosphere of the hot Big Bang? And I come to this question as a result of the previous thinking, but there is a hitherto not recognized foreground, and that those are the forming elliptical galaxies. A whole body of evidence going back to the 1980s, Francesca Mattiucci was a key leader in this discovery, as well as others, have told us that the elliptical galaxies, which we can today touch with the telescope, they are so close, you can resolve them into individual stars, you can take spectra based on individual stars. We know that they formed very early and incredibly rapidly. So this has implications. They are very metal rich. Typical massive ellipticals have supersolar metallicity. To make the metals, you release photons. So for example, the typical proton-proton cycle in the sun makes helium and releases energy, gamma ray photons. And the gamma ray photon. Then we have the CNO cycle in the course of massive stars, and they reduce a lot of photons. We get to high elements by first making C carbon through the triple alpha process, which produces a lot of photons, high energy photons. And so this just tells us the energy release versus temperature in the center of the star. This is the sun, so we are in the PP chain, but then for more massive stars, which have a higher temperature, we get the CNO cycle and the triple alpha cycle. So this burns helium, this makes carbon, and once we have carbon, we make all the other elements through the alpha ladder process. Just build them up in a circle, basically, and each step releases photons, gamma ray photons. There's a hell of a lot of energy being produced in the nuclear reactions, which is why stars shine. Nothing new. We know this is now the distribution of elements, so number of nucleons in nucleus. So we have here, we release energy. This is the average binding energy. So we actually release energy making these nucleus because we build up binding energy up to the iron peak. And any other element beyond that is actually not produced in stars anymore. It's a result of some catastrophic events. But this is exothermic, and that's why stars shine, up to here. Up there, that requires energy and makes stars unstable. So up to here, we can produce in massive stars, and they are very luminous because of these reactions. So 10 to 100 solar mass star has a luminosity of 100,000 to 1,000,000 solar luminosities. And now look at an elliptical galaxy. That's today at redshift 0. We know from the properties of the stars that it formed in less than 1 billion years, so it's a massive elliptical, and extremely early. I'll come to some times a bit later. They contain about 10 to the 10 solar masses in metals, for example, iron. So you can actually directly calculate how much luminosity they released when they were forming and synthesizing these elements. And to produce this within less than 1 billion years, they were as luminous as 10 to the 15 solar luminosity. That just comes from the nuclear reactions. This is not a number you invent. You do the calculation. You need to go up to iron. That's the luminosity you get. Only possibly the IMF was dominated by hosts of stars.
5 minutes.
Okay, so yes, so they must have formed very quickly. They are very metal-rich, so they must have had a top-heavy IMF, and we know that the more massive ellipticals form faster because they have a high alpha over iron element ratio. So these formation times come from Mond models of just collapsing pregalactic gas clouds. You get exactly the times you deduce from chemical properties. Here's now an example of the work of Yagate-san et al. Recently. The star formation started in the center before the Big Bang. These are just the fits, stellar population models fitting per pixel, and they get ages which started, the galaxies existed before, started to form before the Big Bang, right? So this is the growth curve, the mass. That's the hot Big Bang at this time, and you see that these growth curves started before then. That's just the solution from stellar population models, which we trust, because that's nuclear physics. We trust them reasonably well. I would not say this is proof that they formed at that time, because there are still uncertainties. But it's interesting that this is just the result one gets by doing this analysis, given currently known stellar physics. We observe these very high star formation rates of 1,000 to nearly 10,000 solar masses per year at high redshifts. So this paper, so these are star formation rates observed for galaxies which are approaching the mass of an elliptical galaxy. Here, 10 to the 10 solar masses, and you see this is what one finds at a high redshift. So all of this is not exotic, it's not speculative. This is just real data telling us these galaxies formed. This is the main sequence of galaxies. And so the IMF was top-heavy, and I'm sorry I'm sort of going, but I just want to say, so we checked independently the luminosity of the galaxy, so they started forming, then they build up luminosity, independent calculations. You see you're at 10 to the 15. Just you need that to make the metals. Starbursts radiate at 0.1 millimeter, that's the dust. Orders of magnitude more than in optical frequency. You don't see any of that. A starburst you don't see because it's in dust, but it's radiating like mad at that rest frame frequency. If the galaxies, so we know the spatial distribution of galaxies today, you go backwards in time, you know how close they must have been in order to form, because you know the collapse radius when they're formed in a Mond model, which is the relevant model here, and they must have formed at a redshift of about 18.75 typically. Remarkably, you redshift this to that redshift, and you get a peak exactly where the CMB peak is at 1.9 millimeters. The CMB peak is the formation of elliptical galaxies. It's not the photosphere of the hot Big Bang. Of course, there are big questions. Why is it a perfect black body and so on? I know. And this is where I will then end, because we basically have just this quick graph here. Now I'm just racing through. Planck CMB is not hot Big Bang. The important graph is this one. So we have here the CMB, what we think today, radiation gets redshifted, but then ellipticals form. And they contribute photons, which actually are exactly the same order of magnitude as this. And today what we see as the CMB is actually completely accounted for in terms of the photon energy density, by the elliptical galaxies when they were forming. And so there's an asymmetry in the sky which remarkably matches to the elliptical galaxies. So there's an overdensity of elliptical galaxies. In the southern hemisphere, it's a huge significance. And that's also seen in the Planck data, that there's an overdensity, there's hotter CMB there, and that's where apparently the elliptical galaxies also dominate. So there's actual evidence that this might be the more correct interpretation. And okay, so these are the conclusions now. So dynamical friction test excludes dark matter. There are many other tests. Overall, very low probability for the model, lambda CD model, to be valid. Tidal tails of open star clusters give the same story. Gravitation must be Milgromian. And the hitherto not recognized foreground means that the CMB is probably young ellipticals and more in another opportunity, because we are cooking away. And so these are the conclusions. So.
Thank you very much. Let's thank our speaker. We have time for more or less 3 questions, so not too long, please.
Hi, Pavel. A nice talk.
Thank you.
I have kind of a big question. Sorry, everyone. I have a question on the first part of your talk and one on the last part of your talk. So regarding dynamical friction test, I was wondering, when you determine your manager timescales, do you assume that the mass of the satellite remains the same after every? So when you calculate the merger timescale, do you assume that the satellite's mass remains the same as it goes on its orbits, or does it lose its mass?
So observationally, we know that the LMC and SMC are currently falling past. So we take exactly that mass. There's not much mass loss on that part of the orbit, because it doesn't. We're not looking at what it used to look like 5 billion years ago.
Okay.
So you go 1 to 4 billion years back, and there are no solutions for them to have been on orbit with an orbital period of 1 to 4 billion years, because they would have, if they wanted to be on such an orbit, they would have merged today. And in that time, there's not much mass loss.
Okay. So, but if you were to relax that assumption that they are still, is the first infall?
No effect. You're so far away from any possible solution that any mass loss, I mean, you'd have to vaporize the whole galaxies, basically.
Yeah. No, I'm asking this because earlier works by Boyle, Cochin et al., they had shown that because Chandrasekhar dynamical friction formulation assumes like a point mass, so they don't assume that the mass changes at all. Yeah. If you allow that to change the masses based on the simulations, if you assume dark matter exists, it can change by 70%. So I was thinking if that can...
a long time, but so we do the full life simulations you're mentioning, and so we test these solutions with a full life simulation code. But of course, a full life simulation code takes days if you want to really do it well. And this here with these search algorithms, you only calculate for a few hours to get a full solution space, and then one can select the best solutions and put that into the full life simulation, and then redo the simulation. And this is what we are doing, and which we have done.
Yes.
Okay. As far as I understood, you were very fast in the last part. You proposed that at redshift 18 or something like that, we have a burst of galaxy formation, which will be after that the elliptical current population. This burst is first in the dusty regime, but dust evaporates and then galaxies appear normal. So in this case, we should observe in the galaxy stellar mass function in James Webb, Hubble Space Telescope, at redshift 10, 9, 8, this population of massive ellipticals which are not observed. You see the fraction of quiescent galaxies as a function of redshift is increasing today, but at these redshifts, 5, 6, 10, is very small. We are not seeing this population of elliptical galaxies that you propose formed very fast at redshift 18. Yes, so this is, I think not consistent with observations. Yes.
This is a very important point, and so they are uncovering more and more fairly massive galaxies at redshift 15. So that's already going that direction. What will be interesting is to calculate the dust emission from the galaxies which are observed and see how that adds, just ignoring the ellipticals. But we've just recently done, or Eda Georgu has done a calculation. In our discussion, this came up. So if we relax this condition and we just say, let's assume the ellipticals form between a redshift of 6 and 20, so any time between then, you still get the same effect, basically. Except the problem then is that you would then expect a peak in the observed background, which would be at not at 1.9 millimeters, but somewhere it's maybe half a millimeter, because it wouldn't be as much redshifted, but you still have the same emission. Because the thing is, those elements exist. To synthesize the elements, you reduce gamma ray photons. That's just nuclear physics. So if you say that is all not observed, can't be real, then you have to start talking to the nuclear physicists and try to understand what are they doing wrong. How come when you produce, when you calculate when you synthesize all the iron, how come you don't get the radiation? That's what you then have to do. I don't have to do it because I trust the nuclear physics. And for me, the question is, what is the high redshift observations actually telling us? Now, it's entirely possible that the ellipticals actually formed, because so the calculation was done in lambda CDM setting, expansions to lambda CDM. We have a new model. We call that the Bohemian model of cosmology. The expansion is different. And when we put the same physics into that model, you don't have the problem when the ellipticals actually form at a higher redshift. And then the question then arises, there are some optical effects in the model which create a fairly uniform background. And so we basically have to change the cosmological model completely and then redo everything to develop a new understanding in this cosmological model.
Yeah. Also, James Webb has for the past year pushed the galaxy duration significantly.
Yeah, exactly. So that's the.
But not at the point to have a.
Yeah, exactly.
Yeah, I have more questions, but no time.
Not so much time because there is another colloquium at Ensenada. So a last question, and we have coffee break. Then you can talk with the speaker. And he will stay until Monday, I know.
Yes, all of Monday.
So you have plenty of time to talk with him. Last question, please.
Okay, certainly a lot of information, very interesting things. Okay, because we don't have time, coming back to the Winnie Pooh, I would be a little bit worried about using Chandrasekhar. As we all know, Chandrasekhar is developed for homogeneous, infinite media. If we are in something like a halo, we have extra effects that are not considered in Chandrasekhar formula that can give energy in both ways. So we all know that delays the sinking time. Maybe it's not enough to explain what you're saying. We need to see all those details. But also you have simulations and body simulations. However, I understand you are presenting a lot of things. You didn't give details of the simulations. For example, it's very nice that you do this exploration of the parameter space. However, I don't know what region, for example, are circular orbits, eccentric, are they bounded, the three of them, only two of them? There are many unknown things that could change things, but I guess it's very nice work. I'm very happy to see that these kind of studies are, so certainly I will look for you and see more details, but we need to be careful with all those details to have this very strong statement, but it's very interesting work. It's just my comment.
You can believe me that we are very aware of what you're talking about.
Okay, we'll see. We'll see.
Very aware.
We'll see.
Thank you. We'll thank our speaker again, and we have coffee and cookies, so we invite the speaker to go and enjoy, and the students are invited.
So there are 6. So these are just in the chat. Cannot hear the question, microphone. Oh, yeah.
They have questions.
So,